Okay, I have another repair video. Unfortunately, it's another power supply. This one's out of an RM Nimbus computer. The Nimbus was an interesting machine. It was built from the mid-1980s, and it went through the 80186, 286 up to the 386. The first one wasn't compatible with the IBM machines, but the later ones were, so it kind of migrated over to almost become a PC. This isn't mine, it's been sent to me for repair. I don't really know what the history of this is or what state it might be in, so the first thing I'm going to do is pop the fuses out and see how they look. They can often give us an indication as to the nature of any failure, and if that doesn't show anything up, we'll get the unit dismantled. So I'll get these fuses out first. Test meter, have a quick look at this. So that one is fine. Okay, that one's also fine. Now of course these may have been replaced by the current owner, but we'll all start going through the same logical process. So next thing is I'll pop those back in and we'll get the unit disassembled. So the next thing we'll do is take the top cover off, have a look inside and see if there's anything obviously wrong. Okay, I've got the screws out. We should now be able to lift this cover off. Nothing obvious at the moment. So I'm looking for anything with a missing top or that's particularly blackened. I can't see anything amiss at the moment. Some strange marks on that capacitor, but I think that's just some goop on it. Okay, so what I'm going to do now is pop this board out and I'll start measuring the obvious candidates. So we'll measure across the power devices and the big capacitors, and look at the power resistors as well, make sure they're still intact. There's a slight bulge on this capacitor, so we may have an issue here, but as I say, I'll go through and we'll do a few tests. If I find anything at this point, I'll get back on camera and point out what I found. Okay, well, I've been having a bit of a poke around in this power supply. The owner did send me a schematic, but he believes it's the wrong one for this board. It's all I've got at the moment, so I'm going to go with it and see what the differences are. It is from one of these machines, but possibly a different version. And poking around, I found a few things that are a bit strange. Firstly, there seems to be a shorted capacitor at the DC end of the board. So if we measure across there, it's showing as dead short. Now sometimes you can read through a diode, and the presence of the transformer can make it appear there's a short where there isn't. But if you swap your leads around and try it the other way around, if that's the case, then it should change, unless of course the diode short circuit. In this case it's the same both ways around, so it's unlikely we'd have transformer windings going directly to the output anyway. So I'm going to start by popping out that capacitor. I'm also going to give the board a really good clean. It's filthy. These power supplies do have a fan in them, and over a period of time it draws air through and deposits a lot of dirt and debris within the supply. So I'll give it a good clean and I can then read the board more easily as well. So I'll get that off camera, get the capacitor out, check that and give the board a clean, and we'll go from there. Okay, so I've cleaned the board and I've gone through and checked the capacitors. Found two that were dead short. As you can see, that one's just a dead short circuit, and the second one is also dead short. These were both on the output side of the supply, so they are these capacitors here, and with these dead short, it's preventing the supply from booting up properly, because one was on the 5-volt rail, and the 5-volt rail is responsible for the feedback through the optocouplers to regulate the supply. So I replaced those two capacitors and powered the supply up, and initially it started working, or at least it started coming to life. I got as far as testing the 12-volt rail. I moved across to the 5-volt rail, but then the supply died and wouldn't come back to life. So what I did then was hook up the individual rails at these points, so just after the rectifiers, to the bench supply, so I could test each of the outputs in isolation, and they work fine. Can't test the 5-volt rail, of course, because it requires the entire loop to be working. Then I noticed on the schematic this component here. These are effectively variable resistors, and they vary based on temperature. And the reason they're there is to give you kind of a soft start option for the supply, so you don't get a huge inrush of current. And their resistance changes as they heat up. And I found a lot of problems on single-sided boards with these, because they do get fairly hot. And sure enough, when I went to look at it, it's loose. And although you probably can't see it, when I rock it about, I can see that it's not making contact with the pads on the board. So what I'm going to do is clean the solder off. I suspect the track's actually broken where the pin comes through, and I'll remake these connections and give it another go and see if we get any further. Okay, so I've resoldered the temperature dependent resistor, so that's now making good contact. Gone through, and as I say, I've checked the 3 output regulators, or at least the plus or minus 12 volts. I can't test the 5-volt fully because it's part of the feedback system for the overall supply. But I have applied 5 volts to the output to make sure the protection circuit isn't kicking in, and also as that voltage was increased, I could observe that the 2 optocouplers were working. So the next thing I'm going to do is apply power to this, to the input, and see if we get any output. Now, it was originally working to a certain extent. It was whistling, there was no output, and then it would die, and that could just have been the temperature dependent resistor failing to make proper contact. This sort of thing can damage these supplies. They don't like being rapidly stopped and started. It can damage other components. So I'll apply power and see how far we get. If you don't have a variac, then the best thing to do here is to actually feed DC into this from your bench supply with a little very low current limit. Don't just put mains on this, because you'll probably blow something up if there is a fault on it still. These will normally start up around 30 or 40 volts, so if you have, say, a 40 or 50 volt DC supply, then you can use that. I'm actually going to hook it up to the variac here, because I've got one and it's convenient, so I'll get that connected up. Okay, so I've got the supply connected to the variac. We'll bring in the test meter so we can check the output voltages if there are any, and we'll power it up. Now we should see about 150 milliamps on the current meter on the variac. Now again, you probably can't see the current meter for some bizarre reason. My camera can't pick it up properly, but I'll let you know what it says, and we'll see what happens. I mean, obviously if we get a very high current, I'll turn it back off fairly quickly, and we'll start to increase. Okay, it's not looking good so far. Getting very small current drawn, about 10 milliamps, and that is more indicative of the bleed resistor that's across the input capacitor. So I'll just check the output, see if we're getting anything at all. I'll just go into the output socket here. So there's nothing on that one, nothing on that one, and nothing on that one. Okay, so no output whatsoever. We can test the voltage output on the main smoothing capacitor and see if we're getting anything there, and we are. So we're getting 175 volts with 126 volts in, so it does look like we are getting the rectified DC. So the next step is usually where people give up on this type of supply. They can be tricky to work on if you're not used to them, but I'll just go over some general rules for how to go about fault finding on these. If you're familiar with this already, you might want to skip this part. But in essence, they work in one of several ways, and the first thing to do is determine the type of supply that you're dealing with. They normally run in one of three different modes, but if you remember at the start of this video I showed this diagram. Now, as it turns out, this is completely the wrong diagram for this supply. Firstly, you'll notice there are some ICs and optocouplers down here that don't appear on this. However, this doesn't mean this diagram is completely useless. What I did notice is that the input stage, although it's not wired anything like this, is the same mode of operations. In other words, we can use this as a general guide for the mode of operation for this supply. And so the way this supply works is we have a single chopper transistor that's used to put energy into the core of the main transformer. And it does that by essentially connecting the full supply across one of the windings. Now, I did check as part of the initial fault finding that the windings were all intact, or they seem to read something sensible anyway, so it doesn't mean, or doesn't guarantee the transformer's okay, but it's a fairly good sign. They normally go open circuit if there's an issue, or you get shorting between the input and output side, and again I checked for that and it was fine. A bit of leakage, but nothing major. I've checked these output stages as far as I can, so I know that there is nothing dead short on the output. I did find some shorted capacitors which I replaced. But the next thing you have to do is figure out the method that the supply uses for feedback, and this is where they can appear to get quite complicated. This one's got quite a complex feedback path, and it doesn't really matter how complicated the feedback path is. You can resolve it down to the output of the optocouplers. And in this case, I monitored the voltage on the optocoupler as I applied voltage to the 5-volt rail, and they appeared to be doing what you'd expect. They were turning on slowly as the voltage on the 5-volt rail was increased, and that's what they're supposed to do. As long as they can turn on and off, then chances are they're working fine. Again, it doesn't guarantee anything, but it's a first good step. You can quite easily take these out and test them, but I'm not going to do that at the moment. If I need to later on, I'll take them out, but for now I'm going to assume they're working based on the testing I did previously. So the next thing we do once we've determined the mode of operation and the method of feedback, and the method of feedback will be either something like optocouplers or a transformer. So bear in mind the whole principle of this type of supply is that there are two halves to it. We have the input side, which is usually derived from the main supply, turned into high voltage DC, and then that is used to supply power through some sort of isolated system to the low voltage DC output side. And then all the connections between the two sides should have a high degree of electrical isolation, hence the use of the optocouplers. So you'll find that it will either use optocouplers or maybe a feedback transformer, and once you've figured out what each of the main components does, then fault finding becomes much more straightforward. What tends to make supplies like this look far more complicated is that when you drive high voltage transistors at high frequency, you really need to include what are called snubber circuits. Now, what snubber circuits do is they control, or rather they redirect current during the switch on and switch off phase of the transistor operation. So when the transistor is turning on, a lot of the current used to turn the current on through the inductor does not actually go through the transistor, it goes through the switch on snubber circuit. And then conversely, when it turns off, a lot of the energy stored in this current loop, as it's been disconnected, does not go through and stress the transistor. It goes through the switch off snubber circuit. And normally it's something very simple, and you can identify those on the diagram fairly easily, which again is why I was using this diagram. Although it's different from this, it gives me an idea as to the type of architecture we're looking at. So this is an example of a snubber circuit, and we have in this example snubber circuits for switch on and switch off. And what they normally consist of is a resistor, a diode and a capacitor. And the idea is that the diode and the capacitor kind of take over the current path, and the value chosen for the capacitor determines how long current can flow in that process. And then you get the reverse going the other way. And this capacitor and this resistor are part of the chopping system for this particular supply. So as I say, we can look at the snubbing circuits, and they can cause a problem. They are fairly highly stressed, and if the capacitor goes open circuit, it can cause the transistor to overheat, and if it goes short circuit, it can completely prevent the thing from running. And if you are repairing one of these supplies and you find that you've replaced the transistor which has failed, but it's getting very hot and there's no load on your supply, or it keeps failing for no apparent reason, then chances are one or more of the snubber circuits aren't working properly and the transistor is being overstressed. So the next thing we'll do is we'll just check the transistor. I'll try testing it in circuit first. If we need to, we can pop it out of the circuit and test it in our trusty transistor tester, or of course we could use our cheap Chinese variant if we wanted to. Okay, so I'll just flip the board around so we can access the main chopping transistor. So that's this device here. We'll bring in our test meter. I'll put it into diode test mode, and we'll attempt to test this transistor. So we'll go from the base to the collector and emitter, and that looks fine. Reverse the leads. Okay, and that looks fine. We'll check for a short between emitter and collector. It's fine that way around. What we're seeing is a junction value because there are diodes across these terminals, but what we don't want to see is a dead short, and also of course that should change depending on the orientation of our probes. So this transistor looks fine. As I said, we could pop it out and examine it further if we suspect it was faulty. I'm going to assume it's working fine based on these tests, but if I can't find anything else, then I'll pop it out and test it. It might be it's breaking down at high voltage, but the next thing to do is look for another cause. I don't believe this is faulty. Also, if it was breaking down at high voltage, chances are it would have destroyed itself by now, and it hasn't, so I think it's actually fine. Again, the reason for looking at a diagram that's incorrect is it kind of acts almost like a prompt for things to check. The next thing we need to look at is the switch on. I've noticed that, well, you probably noticed as well, that it did nothing at all. There wasn't any click or beep. There's no clicking from this, and if it was trying to start up but there was a fault elsewhere, you'd normally hear them clicking as they continually try and start up. Now that startup phase is normally controlled by in this case, a base bias resistor that supplies current for the initial switch on. And because nothing is being drawn at all, I suspect that we're not getting the switch on pulse required for the basically the oscillation to start up. It won't start on its own because it's driven through feedback from the transformer, and it's feedback from the transformer that causes the transistor to turn on and off. So we have this winding here that causes the transistor to turn on and off. But for there to be anything on this winding at all, then of course the transistor needs to initially turn on. And that's where this resistor comes in. So it's connected from the raw supply, and it's used to initially turn on the transistor to get the oscillations to start up. And we know that in this supply the temperature dependent resistor was just loose on the board, so this resistor would have been fairly highly stressed because the supply would have been constantly trying to start, stop, and that puts a lot of energy through this resistor. And it's the first thing we'll look at. We'll check this. They do have a tendency to go open if you get faults elsewhere, and the same if you get shorted outputs. It can actually cause this resistor to fail simply because the supply is constantly trying to start up, and that start process can kill this resistor. It's only meant to be a fairly low duty cycle, but if there's a fault with the supply, then it can be very highly stressed. So we'll try and find that first. As I say, that's the wrong diagram, so we'll need to try and search out the correct resistor on this particular board. It's going to be a high value resistor, so we've got about 380 volts on the input side, and we need a few milliamps. So you're looking at something usually between 150 and 330 K, and we've got a couple of 100 Ks here, but they are across the two capacitors, so they are bleed resistors. That's probably what was drawing the 10 milliamps that we saw. So I suspect that this is our culprit. Go back to ohms, 220K. Normally they go high or open. This one appears to be completely open. I can't get anything on it at all. Okay, so our first guess seems to be correct, that we have an open circuit resistor, and as I say, that is the resistor. You just check to see where it's going. Okay, and it is indeed going through to the transistor startup circuit. So I'll change this resistor. Now it looks to be a 1/2 watt resistor. As I said, these do get punished if there are issues in the rest of the system. So what I normally do is put a 2 watt resistor in place. It never should dissipate that amount of power, but the impulse it gets during startup is sufficient to destroy 1/2 watt resistors. So 2 watts tend to be far more reliable and make the overall operation of the supply more reliable. So I'll go and dig one out, get this resistor swapped out, and we'll carry on with our testing. Okay, so I swapped that resistor. A new one fitted. As I said, I fitted a 2 watt resistor rather than the 1/2 watt. That will hopefully make the supply much more able to withstand any issues that it might encounter. Given the underside of the board a good flux wash, it was filthy, and next thing to do is to try and power it up again. I did check the surrounding components to make sure that there weren't any other failures, nothing else had been taken out, and I can't find anything else wrong, so we'll try powering this up. Okay, so we'll start to increase the voltage applied, and by the time we get to 40 or 50 volts we should see it kick into life if we've made any improvement. So okay, it's looking promising. We're getting 200 milliamps. It's now dropping 110 milliamps. I'll go up to 100 volts, or at 80 milliamps, and we'll bring in the test meter and see if we're getting any output voltages. Okay, so I'm going to the output connector. We're getting minus 12 volts, 5 volts, and 12 volts. So that's looking very promising. What I'll do now is go through, replace the remaining capacitors As I say, I replaced 2 capacitors that had failed, but there are a total of 5 identical capacitors on the board, and if 2 out of those 5 have failed, then almost certainly the remaining ones will fail as well. So I'll get those replaced. I'll do a full power test on this, and I won't bore you by showing that on camera. I'm sure you've seen enough power tests on supplies recently. So as you can see, they are quite easy to work on once you get the general principles sorted out and you identify what each part of the supply is doing. They do tend to look a bit daunting when you first start working on them, but if you kind of break them down into their individual sections, then you can normally sort the problems out with them fairly easily. Some are more complex than others, but they all do operate in a very similar manner. Okay, I've got it running at 245 volts on the AC input. The current drawn is about 80-90 milliamps, which is correct. The outputs are all correct. And so what I'll do now is get this reassembled into the case. I won't show that. It's obviously fairly dull bolting these things back into metal boxes. And then I'll do a full power test before I send it back to its owner. If anything does crop up as a result of the testing, I'll obviously put that on a video, but I'm fairly confident that this is now resolved and sorted out. And again, hopefully it's evident that these are fairly easy to repair. There's nothing kind of magical about them or particularly difficult. The main thing is really don't apply mains directly to the inputs while you're trying to repair them until you're fairly confident that you've resolved the issues. They do tend to generate cascade failures where a fairly small fault can destroy some fairly expensive devices. And so, as I say, you can run these quite easily from a bench supply, and that can save all manner of aggravation, and it also allows you to use a scope on the input section. Normally you can't use a scope on the input section because it's connected directly to the main supply, which obviously would destroy your scope. But if you have it hooked up to a bench supply, then it is quite safe to use a scope on it. Just remember to disconnect it before you plug it back into the mains. Okay, so that's it. Any comments are welcome. If you want to see more detail on future repairs, and let me know. If you want to see less detail, let me know, and hopefully you found that of some use.